Hello, everyone, and welcome to today's webinar titled Flexible Pavement Design with Geogrids, Design Theory, Technical Basis, and State of the Practice, Part 1, created and paid for by Tensar and presented by Brian G., Director of Education and Training at Tensar. My name is Brandon Rial. I am the Director of Markets at Tensar and will be moderating today's session. As a quick introduction to Tensar, Tensar International is the inventor of Geogrid and provides full-service solutions for customers around the world. Our products are backed by extensive research, and our highly qualified team of engineers and scientists deliver design and construction support unequaled in our industry. We help engineers, contractors, and owners use Geogrid to achieve more cost-effective, reliable solutions for pavement construction, soil stabilization, and earth reinforcement, and other site development challenges. As we go through this presentation, you'll have the opportunity to submit questions or comments to Brian and me by typing them in the questions box of the control panel. You may send your questions at any time during the presentation. We'll collect these and address as many as possible during the Q&A portion at the end of today's presentation. The PDF of the presentation is available to download now under the Handouts tab of your control panel. Also, please note that a PDH certificate will be sent to you from Tensar following this presentation. With this, I would now like to introduce today's speaker, Brian G. Brian is the Director of Education and Training at Tensar, where he has worked in many positions from sales, product management, and marketing. He is a licensed professional engineer and received his BSc and MS in Civil and Environmental Engineering from Duke University. He is also the Executive Council Chairman of the Geosynthetic Materials Association. And with that, I'll go ahead and turn the time over to you, Brian.
Thank you, Brandon. Let's begin today by reviewing our agenda, and also for the second part of this two-part series, which will be presented on June 9th. Today, we'll focus on the fundamentals of how geosynthetics in general and Geogrid in particular function to improve the performance of roads. We'll start by defining functions, materials, and mechanisms, and establishing the distinctions among them. Then we'll focus on Geogrid and take a detailed look at how it provides the function of stabilization, which is the critical function for improving the structural capacity of pavement structures. Then we'll shift to an overview of pavement design, which will set us up for a much more detailed discussion in part 2 on June 9th. Finally, we'll finish today's session by summarizing what we've talked about and providing a preview for the topics for part 2. When we resume with part 2, our discussion will cover flexible pavement design and how to incorporate the benefits of Geogrid, or any geosynthetic for that matter. We'll review the research and performance validation testing, which provide the quantitative basis for these designs, and we'll briefly discuss the need for effective specifications to ensure the performance of constructed projects. We'll then finish up with an overall summary and recommended practice for the subjects we've discussed in both part 1 and part 2. To start, we'll discuss some fundamental terminology regarding geosynthetics. The use of some of these terms has evolved over the years, and in some cases continues to evolve as additional research helps us understand more about how these materials work. Here we'll establish these concepts as they are currently understood and will be used in this discussion. I'll start with the definition of the term geosynthetics. Geosynthetics are synthetic products, usually but not always including polymeric materials, which are used to solve civil and geotechnical engineering problems either in or on the ground. They do this by either adding to or enhancing the functions of conventional construction materials like soil, stone, concrete, and asphalt. This allows construction to be more efficient, cost-effective, and reliable. Now we'll take a look at the functions of geosynthetic materials. It's critical to understand each of these functions and how they are provided by the various geosynthetic materials. In many cases, these functions can be provided by more than one type of material, and some materials can provide multiple functions. For any project, the key to successfully using geosynthetics is to adhere to the concept of design to function. That is, to thoroughly understand the functions of each material selected, and then to connect those functions to the engineering objectives. This seemingly simple and fundamental concept of design is sometimes, for a variety of reasons, not well applied to the use of geosynthetic materials, which can result in negative results. The 7 primary functions of geosynthetics are listed here: separation, filtration, containment, stabilization, reinforcement, drainage, and protection. We'll discuss 4 of these in detail on the next few slides. In the diagrams used in this presentation, the geosynthetic material is represented by a black line, water or other fluid is represented by blue arrows, and forces such as loads, confinement, and tensile stresses are represented by red arrows. Note that this discussion is focused solely on the functions to be provided by the geosynthetic. The specific type of product to be used is held for later. Separation and filtration are often used interchangeably. My view is the best way to understand this is that we want to achieve separation by using filtration. What we're talking about is restricting the movement of some materials while not necessarily restricting others. Specifically for a road, we want to restrict fine-grained subgrade soils from contaminating our aggregate, but we don't want to restrict movement of water that might be in the subgrade because that can create other problems. With geosynthetics, there are a couple of ways we can go about this using either geotextiles or geogrids, but they achieve it differently. This is the source of quite a bit of misunderstanding because geogrid has large apertures. The fact of the matter is filtration is achieved differently with geogrid than it is with geotextiles. While a geotextile uses the geosynthetic material itself as a filter, a geogrid works with the aggregate particles which are confined in the apertures to create a filter. Both have limitations and both must be properly designed to successfully achieve filtration. There is no one-size-fits-all answer for filtration. This topic is beyond the scope of our discussion here, but I invite you to check out the resources on our website, our professional education portal, and our blog, where we go through the design of this function in detail. Reinforcement provides additional strength to a soil mass to resist stresses which are constant and relies on the in-plane tensile strength of the geosynthetic. The various types of stress that are applied to a reinforced soil mass are translated into tensile stress on the geosynthetic. The most common application for the reinforcement function is in reinforced walls and slopes. Stabilization is the function of preventing movement of granular materials when loaded perpendicular to the plane of the geosynthetic, resulting in increased stiffness of the granular material. Stabilization is often confused with reinforcement. For many years, the distinction between the two functions was poorly understood and the terms were used interchangeably. But recent research is demonstrating that they should be considered separately. The key distinction is the difference in loading conditions. Stabilization enhances the performance of granular layers when loads are applied intermittently and perpendicular to the plane of the geosynthetic. The most common application of the stabilization function is to enhance the performance of aggregate layers in roads. Drainage is the function of collecting fluids, usually liquids, but sometimes gases, and allowing them to flow in a desired direction. Flow occurs either within the geosynthetic or along its plane. There are numerous applications where it is critical to avoid the buildup of fluid, usually water, to maintain the integrity of a system. Geosynthetics are often used for this purpose. Now that we've reviewed the functions of geosynthetics which are applicable to roads, let's look at the categories of materials that provide these functions. The broad category of geosynthetics includes numerous materials that are quite different from one another. The 5 categories shown here cover the majority of geosynthetic materials, but even within these categories, there are significant differences among the various products. Here are some of the primary applications of geosynthetics. For the remainder of this session, and in part 2, we're going to focus on roads and pavements. We'll start that discussion with some work by the U.S. Army Corps of Engineers, which has identified 3 performance mechanisms to describe how geosynthetics improve the stability of granular materials in a road: tension to membrane effect, improved bearing capacity, and lateral restraint. The following diagrams from the Corps help describe each of the mechanisms. The tension to membrane effect is the first mechanism identified by the Corps. This mechanism applies primarily to geotextiles used over soft soils and has limited applicability to geogrids. When tension is introduced in the plane of the material, either by stretching and anchoring it or due to rutting as shown here, it creates vertical support for the layer above. This is the mechanism which is modeled in the Giroux-Norey method published in 1981, which was one of the first robust design methods developed for gravel surfaced roads over soft subgrades, combining a theoretical analysis with full-scale empirical testing. Giroux-Norey dealt exclusively with geotextiles and demonstrated the effect seen here very clearly. That is, the tension in the fabric due to rutting creates vertical support. It should be noted especially that the rutting seen in their testing was as much as 11 inches deep. This is the least relevant of the three mechanisms for permanent roads, particularly for geogrids and over strong subgrades. The second mechanism is improved bearing capacity. This mechanism describes the ability of a geosynthetic to spread loads over a wider area, which reduces the pressure on the subgrade. This mechanism is analogous to the way a snowshoe allows the wearer to walk on top of snow without sinking in. In fact, it is often referred to as the snowshoe effect. The third mechanism identified by the Corps is lateral restraint. This applies specifically to geogrids and refers to the ability of the grid to confine aggregate in the grid apertures so that movement of the aggregate particles is restricted. The particles that are confined by the grid also interlock with the particles above the grid, creating greater stiffness in the layer as a whole. Lateral restraint is the most important mechanism related to geogrid performance in road applications. I'll complete this portion of the discussion with the principle of designing to function. This simply means knowing what you are trying to accomplish and selecting materials accordingly. It's also important to use appropriate design methodology for the proposed application. As an example, the Giroux-Hahn method for designing gravel surface roads over soft subgrades was developed with a traffic limit of 10,000 passes, while AASHTO methods for flexible pavements are valid for millions of vehicles over many years. It would not be appropriate to use the two interchangeably. In most cases, there are well-established design methods that are endorsed by independent authorities. These may need to be adapted for innovative materials, but you should always ensure that the underlying approach is valid. Similarly, make sure you understand which material properties affect performance. These will be design inputs, and which serve as quality control measures only. Most design methods for geosynthetics in roads are empirically based, so make sure there is sufficient performance validation testing on the materials you specify, and make sure that testing is reflected in the design method you're using. Now let's turn specifically to geogrids and how they're used in stabilization applications. The category of geogrids includes materials that are manufactured in different ways for different purposes. Geogrids are used to provide the functions of reinforcement, stabilization, and in conjunction with a properly designed granular layer, filtration. They can be manufactured as integral products produced from a polymer sheet. This is the tensar process, woven from polymer fibers that are coated for durability, or produced by gluing or welding individual polymer straps together. Some geogrids are designed to provide high tensile strength in the plane of the material for the function of reinforcement. These are referred to as uniaxial geogrids and are usually either integrally formed, as in the top right photo here, or woven from polyester fibers, as in the bottom right photo. There is also a special category of reinforcement geogrids made from high tensile strength materials, including fiberglass, that is used to reinforce asphalt for increased fatigue resistance and crack control. These are referred to as asphalt interlayers and are not shown here. Biaxial and multiaxial geogrids provide the functions of stabilization and filtration. The left side photos here are examples of integrally formed biaxial and multiaxial geogrids manufactured by Tensar. All design methods for geosynthetics and road applications developed to date are based on empirical testing. The nature of these applications and their construction, along with the natural variability of materials such as soil, aggregate, and asphalt, make it impossible to accurately determine performance based on the materials themselves. This is why it's impossible to correlate specific material properties, such as tensile strength, with performance in a road. Instead, we rely on full-scale moving wheel tests, which generate large quantities of data that allow us to analyze performance probabilistically. We'll see in a few moments how AASHTO design methods for pavement use this approach. But for now, let's look at some work done at the Transportation Research Laboratory, or TRL, in the UK, to learn more about how geogrids work in these applications and the differences between stabilization due to interlock and tensioned membrane reinforcement. There have been 10 separate TRL test programs on geosynthetics running from 2001 to 2014. We'll review one of them, comparing a high-strength woven geogrid with an integrally formed geogrid. There are 4 charts here. The top 3 each represent a cross-section across the wheel path. The vertical axis in all charts is rut depth in meters. The chart on the top left is a control section without any geogrid. The top middle has a woven type geogrid. We've labeled this membrane. The top right has an integrally formed tensar geogrid. We've labeled this confinement. In each of these charts, the top line shows the surface of the granular layer, which is a 300 millimeter thick aggregate. The lower line shows the top of subgrade, which has a strength of around 2.5% CBR. The bottom chart will show the mean rut depth for each section as rutting develops. The horizontal axis is the number of wheel passes. After 100 passes, we see small ruts starting to develop in the surface of the control, but also on the subgrade level. After 200 passes, the rutting is progressing in the control and is just becoming noticeable in the membrane section. Let's click right through to 10,000 passes. 500, 1,000, 2,000, 5,000, 9,000, and finally 10,000 passes. After 10,000 passes, the control section has deep rutting and heave at the surface. Trafficking of this section was stopped at 2,000 passes when rut depth exceeded 140 millimeters. The membrane section has developed pronounced rutting with heave on either side of the ruts. Surface rutting is 100 millimeters. There is also significant rutting in the subgrade that mirrors the surface profile. In contrast, the confinement section has much less surface rutting, only 60 millimeter rut depth, and virtually no deformation at the subgrade level. It's important to note that the woven geogrid membrane product used here has twice the tensile strength of the confinement geogrid. The TRL program and other research work has proven that tensile strength is not an indicator of performance. In 2006, Drew and Hahn published this chart as part of the discussion enclosure related to their design method for unpaved roads, clearly indicating that strength is not an indicator of performance. The vertical axis is traffic benefit ratio, a measure of the performance of geosynthetics in a road structure. The horizontal axis is the tensile strength of the geosynthetics. There is clearly no relationship between strength and performance. If you look at the products at 20 kilonewtons of strength at 5% strain, they cover the full range of performance, low to high. There are also high strength products that are clearly outperformed by lower strength products. Unfortunately, this clear message is still not understood by many suppliers and specifiers of geosynthetics. That same year of 2006, at a Geosynthetics in Roads workshop in Jakarta, Dr. Drew made a similar point in relation to the performance of geosynthetics in paved roads. He was very clear that membrane function was not relevant, and only lateral restraint or confinement is effective. These are his slides. A key point here is that the aim is to have small deformations or rutting. He's also clear about the importance of interlock for lateral restraint. This diagram shows how the inclusion of a geogrid can influence the behavior of granular materials some distance above the geogrid location without the geogrid deforming. What is this chart telling us? The aggregate interlocking with the geogrid is confined, but the aggregate above that layer is also confined. Maximum confinement occurs close to the geogrid and reduces with distance from the geogrid. Close to the geogrid, we have a zone of maximum confinement. As we move away, we have a zone where there is partial confinement. Eventually, we will reach a layer that is too far from the geogrid to be influenced by it, and there is no confinement. The performance of the composite layer will depend on the magnitude and depth of the confined zones. These will depend on the confinement efficiency of the geogrid. How do we prove that the geogrid has an effect within the zone of confinement? One piece of research by Professor Horváth at Győr University in Hungary is very useful for demonstrating this effect. Professor Horváth constructed a multi-layer shear box capable of sliding at various levels. A test section was constructed with a subgrade in the lower part and aggregate in the upper part. A geogrid could be included at the interface between aggregate and subgrade. The box could then be sheared at various levels, starting at the top and then moving down in 100mm stages. The force required to shear the box is measured in each case. In the chart here, we see typical results. The vertical axis is the level above the grid location. The horizontal axis is the peak shear force. The dotted line is without geogrid, and the solid line is with geogrid. The difference, or shift, represents the geogrid effect. We can see that there is an effect extending up to 300mm above the geogrid location. It's important to remember that the geogrid remains flat throughout, in contrast to the tension membrane reinforcement effect, which required deformation of the geosynthetic in order to reinforce. We've also replicated this type of test using discrete element modeling, or DEM. DEM uses small spheres to model materials in a computer simulation. The soil is first modeled by replicating the size and shape of particles and combining the correct grading of the particles to create a soil and an aggregate mass. The geogrid is modeled with an approximate geometry, and then the models are carefully calibrated using physical testing. The next stage is to construct the shear box model. The model here comprised a clay subgrade and an aggregate layer. A geogrid can be included at the interface. The results in the chart are very similar to the Győr curves, and the geogrid stabilization effect is again clearly demonstrated. The same DEM modeling technique has also been used to simulate a moving wheel over a stabilized layer. The model simulates trafficking with a wheel traveling up and down over granular soil on a soft subgrade. The model allows us to look at loads and strains in the geogrid ribs and displacements of the aggregate particle and much more. Since we are focused on stabilization today, let's look at particle movements. We're looking at two cross sections of the model across the direction of the wheel path. The upper section is a control without geogrid. The lower section has Tensar TX160 geogrid. The color scale indicates the magnitude of particle movement under load. Dark blue is no movement, through green to red, illustrating maximum movement. We clearly see that the geogrid is controlling particle movement, reducing the number of particles moving around above the geogrid and reducing the magnitude of particle movements. This is stabilization. Let's look at one more way to visualize stabilization. Andrew Lees of Tensar has provided us with an alternative explanation of the stabilization mechanism, which I think really helps us understand how stabilization works. In this explanation, we consider the particles making up the aggregate layer. All particles are in point-to-point contact with two or more other particles. A load applied at the surface is transferred by particle-to-particle contact. The load is carried along preferential paths or force chains. If a particle moves under the forces applied, then load will be shed to adjacent particles until equilibrium is achieved. It's possible to view force chains in a model using photoelastic disks that change color under stress. The chains of force are clearly seen in this model using the photoelastic discs. Forces are transferred by particle-to-particle contact. Compaction brings about a degree of stabilization by causing this to happen. It reduces the potential for particles to move and rotate, which stiffens and strengthens the granular layer. The particles between the force chains are also important. They're preventing the chains from buckling. A column of particles stacked up under load would not be stable by itself. Here we see the force chains again in another photoelastic disc model. We can see a buckled force chain on the right. You can just make out the faint buckled force chain. If a force chain buckles, load will be shed to the next chain. The effect is that the remaining force chains are becoming more vertical and the loaded zone at the bottom is getting smaller, increasing stress on the base. This may lead to punching failure in a subgrade. As particles are being rearranged and displaced, the granular layer has less stiffness. This will result in the surface deforming or rutting. If we want to stop this from happening, we need to hold the particles in place. How? Well, we could fill the voids with glue. That's what we do with cement or lime stabilization of soils. The particles are then fixed together and movements controlled. This is how chemical stabilization works, but it has many other drawbacks. So how do we achieve the same thing with Geogrid? Here's the same image. If we introduce a layer of Geogrid at the bottom, the particles interlock with the grid and a zone of confinement is created, as we saw earlier. The particles are restrained and buckling of force chains is inhibited. We might add a second layer to increase the effect. Then we have a fully stabilized layer. Now let's look at stabilization versus reinforcement functions in a pavement design. If the capacity of the stabilized layer is exceeded, the stabilization effect is overcome and the layer will deform. Strains in the geogrid will then increase and surface deformation or rutting will increase and become unacceptable. By then, the road has failed. We therefore design for the stabilized, low strain condition. Beyond that, we consider the layer to have failed. Those who insist on specifying ultimate tensile strength and ultimate strains, or even specifying load at strains 2% and 5%, are designing for a failed condition, therefore, way beyond the serviceability limit of a road. Stabilization is about controlling the movement of particles and limiting deformation. That is the only suitable approach for permanent roads. So to summarize, the importance of stabilization as the primary function for improving road performance. Efficient confinement and control of particle movement results in small surface deformation, improved layer stiffness, and increased bearing capacity. And a low deformation, low strain condition is essential for pavement performance because greater deformations mean the road has failed. Having focused in on stabilization using geogrid, the next question is how different geogrids, even integrally formed geogrids intended for stabilization, compare in performance. Is one geogrid the same as another? To answer this, we'll look again at geogrid under a wheel load. These pictures are from a test rig at Tensar's lab in the UK, where we can simulate field conditions to test products. We've placed a compacted gravel layer over a soft clay subgrade and then repeated the setup, adding 2 different geogrids. Then we load the wheel and run it back and forth over the test section to simulate traffic. Here's what the gravel surface looks like after 1,000 passes of the wheel when no geogrid is used. You can see that a significant rut has developed and the material at the surface has been pushed to the side. This photo shows the results when one of the geogrids was added to the section on top of the soft subgrade. You can see that the rutting is reduced significantly. And here's the section using the second geogrid after it was trafficked with the same loading as the other two sections. A much smaller rut and a more stable surface. So we see a difference in performance between the control and the stabilized sections, and also between the two geogrids. But the real story is beneath the surface. This photo shows the first section, which did not include geogrid, after trafficking and with the gravel layer removed. You can see that the rut from the surface pushed all the way through to the subgrade. If this were the subgrade of a road, rutting like this would cause a failure that would require reconstruction. When the first geogrid is included in the section, you can see that the rutting of the subgrade is significantly reduced. This would translate into increased traffic capacity and life for the road. Now let's look at the section that included the other geogrid. As you can see here, the difference in performance between the two geogrids is dramatic. Not only was the surface rut smaller, almost none of the rutting has come through to the subgrade. Protecting the subgrade like this has a dramatic effect on the life of the road, and it is the result of increased stiffness in the aggregate layer due to better confinement by the second geogrid. Tensar uses this type of testing to continually refine the designs of our products so that they confine aggregate more effectively to improve the performance of the mechanically stabilized aggregate layer. Now that we've covered the fundamentals of how Geogrid functions in road and pavement applications, let's turn our attention to pavement design. For many centuries from the beginning of civilization, the traffic on roads didn't change very much. Horses, oxen, and wagons were the only vehicles. Beginning in the mid-19th century, wheels and then vehicles started to see rapid changes. The evolution of wheels went from stone to wood to iron to solid rubber to pneumatic tires. At the same time, vehicles evolved with the advent of motorization. As engines became more powerful, vehicles could be designed to carry more weight and move faster. And as the automobile took off, more vehicles were on the roads. We began to go faster, we began to carry heavier loads, and we began to do it on tires that allowed the vehicle to move at higher speeds comfortably. You certainly wouldn't want to drive 60 miles an hour on stone wheels, for instance. This set up a sort of circular effect in road construction. Vehicles were starting to move faster and carry progressively heavier loads, so the roads had to get better. But as the roads then improved, it allowed us to move heavier loads even faster. Through the end of the 19th century and into the 20th, loads, speeds, and tire technology continued to evolve, so roads needed to continue improving as well. Looking at pavement structures from the earliest times, we can see two trends. As experience grows and construction methods are refined, typical pavement thickness decreases until about 1900. You see the Roman roads on the left here, and then the Telford design and macadam design are some of the first designed gravel surfaced roads that were created in Europe in the 16 and 1700s, and then moving into more modern design. Around 1900, as traffic volume, vehicle weight, and speed increase, typical pavement thickness begins to increase again to accommodate the greater loads. Into the 1930s, 40s, and 50s, pavement design was still pretty much experience-based. It depended on standard sections and it depended on rules of thumb. Around the middle of the 20th century, some empirical relationships were starting to be developed, which related the required thickness to the wheel load that was going to be applied, the traffic volume, and the subgrade strength. That is, we started to get a real design of the road as opposed to just building a road by rules of thumb or standard section. Early asphalt roads were 9 to 10 inches total thickness, and a modern interstate is significantly thicker than that. So as we continue to carry more and more load, section thicknesses have gotten greater over time through the 20th century. But until the late 1950s, roads were not designed and built with anything resembling our current methods. When we talk about modern, rigorous pavement design, we go back to what's known as the AASHTO road test. AASHTO was the American Association of State Highway Officials. You would now know it as AASHTO because they added the word transportation to the acronym. When you see something from AASHTO, it's the same organization that did this original road test. This road test was conducted in Iowa, Illinois, which, as you can see, is west of Chicago, between 1958 and 1961. AASHTO got together and built a series of test tracks, ran vehicles over them, and collected extensive data to try to develop a design methodology for pavement. Here are examples of what the test loops looked like. In the foreground of the left photo, you see the loop that's the turnaround for this particular test section. If you look further out in the distance, excuse me, you would see another loop where the vehicle would turn around the other way. There were a series of these test loops constructed with varying thicknesses. They were trafficked with various vehicles, and they were measured very carefully to determine how the thicknesses of the various elements and the other components of the pavement impacted the life of the pavement under different vehicle loadings. There were two parts to the test: rigid pavements using Portland cement concrete pavement, and asphalt or flexible pavements. Here you see some examples of what was used in the flexible part of the test. They used dense graded hot mix asphalt, 85 to 100 pen. Pen is a penetration test that determines how stiff the asphalt itself is, not the aggregate, but just the binder. A 100-gram weight on a needle is placed on the asphalt, and the deeper the needle penetrates, the softer the asphalt. In a warm weather climate, one would want to use something with a lower penetration number because you don't want it to soften in the heat, whereas a higher penetration number would be used in a colder climate because you would not want the asphalt to become brittle in the cold. This test has been superseded by the modern designations for asphalt at this point, but the idea is the same. The base course used was crushed limestone. Subbase was constructed out of a sand gravel mixture, and all of the loops were built on silty clay that was the soil in the area. The average subgrade strength was a CBR of 2.9, which is average quality. Most roads today are built on a minimum CBR of 3. The important point here is that AASHTO used a certain set of materials to construct the flexible pavements for the test, and that many of these were quite different from the materials that might be used today across the country. In particular, the asphalt used was significantly less advanced than the mixes that are in use today. The sections tested ranged in thickness as shown here. The asphalt layers range from 1 to 6 inches, the base course ranged from 0 to 9 inches thick, and the subbase ranged from 0 up to 16 inches. The thickest section tested was 6/9/16 inches of subbase, which they tested using the heaviest trucks they had, while the thinnest section they tested was 1 inch of hot mix asphalt directly on the subgrade. That thinnest section only carried 8 to 25 equivalent single axle loads to failure, not a very high capacity road. But this did provide a lower bound for the data, allowing AASHTO to determine design relationships. Here you see some of the pictures of the vehicles that were used in the AASHTO road test. They range from a pickup truck that weighed 2 kips or 2,000 pounds to the heaviest vehicle, which was a 48 kip tractor trailer that you see there on the lower right. The current US federal limit for a tractor trailer is 80,000 pounds. So the heaviest vehicle used here was not much more than half as heavy as what's on our roads today. Yet the majority of pavement design today still relies on the relationships that were developed at the AASHTO road test. There have been refinements to the methods over the years, but clearly there is a need to continue developing newer approaches. At the same time, this shows what a remarkable engineering achievement the AASHTO road test was. This methodology that was developed over 50 years ago with many limitations has stood the test of time and still is the foundation for most road design, at least for flexible pavements. This is the AASHTO design equation for flexible pavements as it exists today in the 1993 version of the AASHTO method. It relates the traffic capacity of a pavement, shown as a number of equivalent single axle loads, or easels, to the structural capacity of the pavement based on the materials used, their thicknesses, and the serviceability requirements of the road. The relationships here are probabilistic. That is, they are established based on empirical data and statistical analysis. As you look through the equation, W18 is the allowable easels, that's the traffic. Z sub R and S sub O are statistical factors that go into the model. Sn represents the structural number, which is a measure of the structural capacity of the pavement. Delta PSI is the change in serviceability from the pavement's condition at its construction to its condition at the end of its useful life. And M sub R shown here is the subgrade resilient modulus, or the strength of the subgrade that the road is being built upon. ASHO developed several important innovations as part of the road test that we still use today. The equivalent single axle load, the easel, was developed during the ASHO road test. The idea behind the easel is that different vehicles have varying impact on pavement life due to the differences in their weights. For example, a passenger car does a lot less damage to a road than a tractor trailer. This is normalized in design by using the equivalent single axle load for traffic. The overall objective of the test was to quantify the relationship between the thickness of a pavement and the performance of the pavement. ASHO developed a measurement called serviceability index, which is a measure of the rideability of a road. As part of the test, they actually went and got ordinary citizens, drove them around the loops, and asked them for their assessment of whether the ride was acceptable or not. Then they took all of that data and scaled it from 0 to 5 in terms of serviceability index, with a perfect pavement being a 5 and a completely failed pavement being a 1. Typically, a pavement that needs to be rehabilitated would be a 2 or a 2.5. So they used the actual experience of untrained people to get an idea of ride quality, and then created a parameter based on the data they collected. Pretty remarkable. ASHO also developed the ideas of the structural number of the pavement and the structural layer coefficients of various materials. These parameters rate the stiffness and strength of the materials used to build pavements to the traffic capacity of the pavement. Different materials have different layer coefficients, and the thickness of a material layer multiplied by the layer coefficient results in a structural number, which we use in design as a measure of the layer's structural capacity. Ultimately, what ASHO managed to do was learn how to statistically model pavement performance by using a lot of different vehicles over a lot of different sections and carefully measuring the resulting traffic damage. This is very similar to what we still do today in our research. Tensar conducts accelerated pavement testing research with the U.S. Army Corps of Engineers and other research partners. DOTs, universities, and other entities conduct similar pavement research around the world. This research is empirical in nature. Actual loads are run over actual sections, and the response of those sections is monitored and measured. The impact of heavy loads merits some additional discussion. We talked earlier about easels and how this measure allows us to normalize the damage done by different types of vehicles. One important thing to remember is that the equivalent single axle load scale relating weight to easels is a logarithmic function. So in the example here, one loaded dump truck on the road is equivalent to putting almost 10,000 cars on that same road. Weight has a huge impact on the wear of pavement surfaces. And for that reason, when we look at design, one of the most important things we have to figure out is how many heavy vehicles are going to use that road. Likewise, anything that can be done to reduce the number of heavy vehicles using a road will exponentially reduce the damage to that road and extend its life. Design has continued to evolve since ASHO published the first design guide from this testing in 1962. The design guide has been revised several times, including in 1972, 1986, and 1993, where they took additional data that had been collected and the collective experience of the different states and rolled it into refinement of the method. We've also learned much better how to characterize aggregate materials and we've developed much improved asphalt mixes, including what's known as SuperPave, which is the current state of the art and allows us to very precisely determine the strength of the asphalt. We have much better paving equipment now than we had in 1958, and geosynthetics have been introduced to pavement design by Tensar and others, including geogrids, geotextiles, asphalt interlayers, and drainage composites. Two of the most recent developments have been the development of mechanistic empirical design methods and the development of in situ test methods. That is, the ability to test the strength of materials after they have been placed in the field, as opposed to relying on previous tests. We'll cover mechanistic empirical design briefly and then conclude our presentation for today. Mechanistic empirical design takes the work that has been done historically by AASHTO, which was empirical, and combines it with a mechanistic model of the pavement. Empirical research has consisted of applying a load to a constructed pavement and assessing the damage from that load. A mechanistic model goes beyond this, in that instead of simply testing the pavement to determine what happens, we actually try to develop a fundamental understanding of how the materials in the pavement relate and react to different factors. Those factors might include the load, but they also include the types of material used, the climate conditions, and others. Implementation of mechanistic empirical design has been an extended effort over many years by AASHTO, and it's now being adopted in several states. Others are moving more slowly to it. This approach takes the expected response based on the mechanistic model and relates it to the empirical damage that has been measured either in accelerated pavement testing or in the field with actual roads. By tying those two together, you have both a model that is now calibrated based on what you're using to build the structure and the actual damage that's been measured in the field. Once these are tied together with the proper transfer functions, we have a much more robust view of how to design a pavement and how it will behave over its design life than we would based only on a statistical or probabilistic model that is based on empirical testing alone. Mechanistic empirical design is now included in the AASHTO Pavement ME software, which is readily available and used by several states. The methodology continues to evolve as more pavement performance information is incorporated. Tensar is actively participating in this effort, and we've developed an ME version of our SpectraPave design software. We can make designs from this software available to those who are performing ME designs and wish to make use of our products. We're also working to develop the information required for incorporating our products directly into other ME software by developing the appropriate transfer functions. It's important to note that these transfer functions are going to be specific to each material to be incorporated, and so extensive testing is going to be needed under all the conditions that go into a mechanistic empirical design model. This has been a very quick discussion of a complicated topic. I'd like to close the discussion by noting some key concepts relating to how we design pavements and define their performance. First, it's important to remember that pavement design is built on the understanding that all pavements will wear out over time. The design life of a pavement is defined as the expected time period from the original construction to a terminal condition, when the pavement must be rehabilitated or reconstructed. We measure this via those serviceability measures that we talked about earlier. We measure that condition of pavements in several ways to determine when the terminal condition has been reached. But pavement of failure occurs when that terminal condition, when a pavement is worn out and it occurs early. Part 2 of this webinar will go into the process of design and determining the expected life of a pavement with and without a geogrid in detail. Please remember, all pavements eventually wear out. We define failure of pavements as when they wear out early, and that's what we're seeking to prevent. So let's summarize key points from today's session and preview part 2, which is coming on June 9th. The category of geosynthetics includes many materials with many functions. I urge you to always think in terms of designing to function. Decide what you want to accomplish, examine the materials to determine which can deliver that function, and design accordingly. Stabilization is the key function for improving pavement structural capacity. It's important to understand which material properties affect performance, and these will be design inputs to the design method that you're using, and which material properties serve as QC or quality control measures only. For instance, tensile strength. Flexible pavement design under AASHTO 1993 is a probabilistic design method using empirical testing to predict pavement performance. AASHTO design relates the traffic capacity of a pavement measured in easels to the structural capacity and serviceability requirements for the pavement. And pavement failure is defined by whether a pavement achieves its expected design life or wears out prematurely. In the second part of this webinar on June 9th, we'll use the fundamentals we've discussed here and move on to the design of flexible pavements using AASHTO 1993 methodology in much greater detail. This will include the process for determining the structural capacity of a pavement, how we enhance these designs using Geogrid, how we quantify the benefits of geosynthetics in pavements to ensure reliable design, writing effective specifications, and an overall summary of what we've covered in Part 1 and Part 2, with recommendations for successful projects. We hope you can join us for that session. If you have questions or would like additional assistance with anything discussed here or anything related to the things that Tensar does, please don't hesitate to contact us. You can always receive support from your Tensar regional manager or local distributor, or through our website at tensarcorp.com. You can also email me directly if you have questions about this presentation or need more assistance. Thank you very much, and with that, I'll turn it back to Brandon.
Thanks, Brian. Great job. Have a whole bunch of questions that came through, and I'll go through as many of these as we can. A couple project-specific type questions. On those project-specific questions, I'll have you reach directly out to Brian or your regional manager for those, just because they may take a significant time to go through some of the design needs. But first question for you, Brian, what is one pass? Is it a wheel going back and forth?
Yeah, the answer to that is it's different depending on the method. So in the unpaved methods, and specifically, I discussed briefly the Giroux-Hahn method. When we talk about passes, we were talking about axle passes of a specific vehicle that was used in that testing. When we talk about, when I talked about passes in the DEM models that I showed, those were passes of the wheel that was in the model that had a specific weight. And when we showed the testing in the UK small scale trafficker, that would be one pass of that wheel. That's distinct from AASHTO, where we design in terms of equivalent single axle loads. So in the case of an AASHTO pavement design, we would convert the expected traffic, and that includes the distribution of traffic between cars, trucks. We would characterize that traffic in detail, and then we would convert that to a number of equivalent single axle loads that would then be used to determine how we had to design the pavement. So it depends on the method. Going forward, we're going to speak, and if you can join us for Part 2, we're going to speak only in terms of easels, because we're going to be focused on the design of flexible pavements.
Okay, thank you. Second question, how thick is the confined zone?
Yeah, I might have brushed over that a little quickly as we talked about it, but in general, there's two things I would say about that. First of all, the level of confinement and the thickness of the confined zone does depend on the efficiency with which the particular geogrid you're using confines aggregate. So a geogrid that is more adept at confining aggregate is going to have a thicker fully confined zone and a thicker overall confined zone. That said, we have measured this for our products, And in general, we would use a confined zone thickness of between 12 and 18 inches for a triax geogrid. In general, we would consider the fully confined zone to extend somewhere between 8 and 12 inches, and the partially confined zone to extend between 12 and 18 inches. If you remember in the example with the force chains, this is not, I'm sort of crossing examples here, but in the example with the force chains, I actually showed a second layer of geogrid introduced higher up in the section. If you're using geogrid in an aggregate section and the thickness gets beyond that 18 inches that I just mentioned, we generally would convert that to a 2-layer system, which would allow us to maintain that full confinement through the layer. Normally, we would put the geogrid at the bottom and we would expect that zone to extend up 12 to 18 inches. With triax, it's generally 18 inches. Once you get to 18, you're going to want to add a second layer in there somewhere so that you maintain full confinement.
Okay, thanks. Next question is, can you explain the difference between a membrane grid and a confinement grid? More of a clarification.
Yeah, absolutely. So the woven and coated grid that was used in the TRL research that I referenced, that was a polyester woven and coated grid. The difference is in the way they are manufactured, but also in the material characteristics. So polyester grids are used very often in applications where tensile strength is important. That is in a reinforcement application. And the most common use of those type of grids is going to be behind a retaining wall or in a reinforced slope. But that is a reinforcement application as opposed to a stabilization application. The difference between the two, between that grid and the stabilization geogrid, has to do with you can feel it if you hold the samples in your hands. If you remember the picture I showed of a polyester grid when we introduced geogrids, it was very flexible. The grid itself had actually kind of folded over on itself just because of the way the picture was taken, whereas a stabilization grid is going to have stiff, stable apertures. That's going to allow that grid to more effectively confine the aggregate and keep it from moving. If you have flexible ribs and you have a flexible geogrid overall, then the only way that you're going to develop that support function is to place that grid in tension. And this will be the same for a geotextile. They work the same way because they depend on the tensile strength. It's not that they don't work, it's that they work different ways, and then we have to make sure we apply those functions in the proper place. Where do we need high tensile strength in the plane of the geosynthetic versus where do we need very efficient confinement of the aggregate so that we get stabilization?
Thanks, Brian. Can you put your slide back with your email address? A lot of folks are asking for your email address.
Yes.
So we can write it down.
Whoops, sorry, one pass, there it is.
Perfect. Well, we probably have time for 2 more. This one is a fairly long question. I'm going to summarize it a little bit. In the research that you showed, it mainly addressed rutting of the asphalt layer or the section. The question at the end is basically most of the research you showed didn't show the other testing that was done, looking at stress strain deflection and such. The question is, by thinning a section based on rutting performance only, you risk premature failures in fatigue. Is this going to be covered in part 2?
The short answer to that is yes. And I'll expand on that by saying I greatly appreciate the question because it points to the fact that this is not simple stuff, right? That this is not a matter of simply sticking a material in there and gaining a benefit and moving on. And we will talk about that in part 2. And if you're familiar with Tensar's design software, you'll note that one of its features is that it changes the approach depending on whether you're dealing with a thin asphalt pavement, a standard asphalt pavement, or a thick asphalt pavement, and it gives ranges of thickness for those because the behavior of that section under load is going to change depending on how thick it is. So Apologize if it seemed oversimplistic here, but rest assured that as we go into greater detail in part 2, we will address that.
Okay. The last question for you, Brian. We have several more we're not going to be able to get to. Apologize to those who sent them in, but hopefully we'll be able to get to you. The difference and advantages between Geogrid and a high strength fabric. What are they?
I want to be careful how I approach this, because I want to make sure that we maintain this sort of focus on design to function. So in a stabilization application, the difference in performance, or the advantages and disadvantages, are one way where the differences may be different in a different application. So I'm going to start with a stabilization function. Stabilization, as we've seen in the research I presented today, relies on the ability to confine aggregate and keep it from moving. And you want to do that without large deformations, because large strains in pavements result in failures, right? The job of the subgrade, if we're stabilizing that, or the aggregate base, if we're stabilizing that, is to support the asphalt layer with very small strains. And if we're going to do that, we have to keep that aggregate from moving from the very first load that's placed on it when the aggregate is compacted on the geosynthetic. A high strength fabric can be used to stabilize soft soils, but it necessarily must rut in order to achieve that stabilization, as we saw in the research from the Corps of Engineers. It's not that it cannot work, it's that it requires deformation in order to engage all that strength that is present in that high strength geotextile. So if you do that in an application where you can tolerate rutting, or where you can apply a load and then deal with the rutting afterwards, once you have a stable surface, then you can get an acceptable result. But in a flexible pavement application, by the time you've achieved that stable surface, you've deformed the geosynthetic, the high strength woven fabric, and so you're going to have ruts in the subgrade. Even if you ultimately end up with a stable aggregate base, your subgrade is going to have ruts in it, and that's going to cause problems. So that's the difference in a stabilization application. Now, there are other applications where I would use a high strength geotextile and I would never use a stabilization geogrid. One example of that would be a retaining wall that's using a high strength geotextile for the reinforcement as opposed to a uniaxial geogrid. So all of these materials have different advantages and disadvantages. The key is to return to the concept of design to function, understand what you're trying to accomplish, select the material accordingly.
Thanks, Brian. I appreciate the time and preparation you put into this. There are a lot of other questions on here, many which relate to design. I believe Brian will be covering that in part 2 as far as placement of the grid. There's questions on software and such, and that will be covered in part 2. If you submitted any questions that you feel you'd like to get answers to, please contact Tensar or Brian directly, and we will get back with you. Just a couple reminders: a PDH certificate will be sent from Tensar to you following this presentation. And then just another reminder, we mentioned it a couple times, part 2 of this webinar series will be held on June 9th at 11 o'clock Eastern Standard Time. Thanks all for attending, and we hope to see you on the 9th. Have a great day.